Okay, you guys, questions on the homework? Go ahead, Chris.
Number 4 on the web work.
Okay. What's the question?
So, I don't know, I'm just not getting it. So since we're expressing it in terms of vector I, vector j, we can sort of replace those with dx and dy, and do our usual like p and q thing. But if we take the derivative of 8 sine y in terms of x, it just goes to 0, right?
So you've got p here and q here.
Right.
Q sub x is 0. P sub y?
It's 3.
It's 3. So the integrand becomes negative 3, right? In the Green's theorem, in the area integral?
Yeah.
That's really nice. We like constant integrands. Why? They're easy because you can take that constant out. What's left behind is just the area of the region. And the area of this region, your numbers may vary, but let me think about it. Looks like 4 by 6 for me. 24, and then times another negative 3. So that would be the, I'm guessing that's probably similar to what happened with yours. So just be careful. Be careful with minus signs, right? Because it is qx minus py, and so you could run into, you could be off by a minus sign. If you continue to have trouble with it, let me know. Other questions? Nick?
This is just a side note, but it looked like when I logged on that next class's web work is due at 5 a.m. and not 5 p.m.
That's entirely possible.
Really early definition.
Yeah.
Better get on that.
I could leave it. So let me go down here and yeah. And here, this is a fairly clunky interface, but you know, it's free. I like free.
Do you just like enter all of that stuff?
Depends on what you mean by all of it, but no, it's not as bad as it looks. Okay, so that's fixed. Thanks, Nick. Other questions? Go ahead.
Can you show us how to set up the 3 splits?
Sure. Back to homework sets here, and now it's due at 5 p.m. Yay. Number 5, you said? 3. Sound like a holy grail. You guys don't know Holy Grail, do you?
What?
Some of you do? Yeah. Okay, cool. 1, 2, 5. 3, sir. You know, with the holy hand grenade? Yeah.
Mine will be right up.
Exactly. Okay, 1, 2, 5. 3, sir. 3. Throws the hand grenade. Okay. What about this one? Set it up? So I gave you a hint about how to parameterize this, right? How did you end up parameterizing this curve? Am I asking the wrong person?
Yeah.
Craig?
I got cosine cube, sine cube.
Yeah, so let me go back over here. In fact, let me get this flattened out so I can write on it. So this curve, x to the 2/3 plus y to the 2/3 equals 1. I don't know exactly about this curve, but I've seen curves like it, and it sort of does something like this. Yeah, and I think I did it wrong down here. Anyway. So yeah, the parameterization. And I guess a quick way to double check that this is the right parameterization is to simply substitute it back into the equation and show that it solves the equation, that it satisfies the equation. So if I take cosine cubed and drop it in here, I get cosine squared. If I drop sine cubed in here, I get sine squared. And so yeah, the Pythagorean identity it holds. So now it's a matter of executing this integral. And this is in the Green's theorem section. And one of the things that we learned about Green's theorem, let me just write the general version of it first. P dx plus q dy. So one of the things that we did last time with Green's theorem is we came up with lots of combinations to make this equal to 1. And what was the reason for that? Why is it nice to have that have that 1? Because then it turns into this nice geometric notion of area. So if this is 1, then this becomes the area of D is equal to whatever this is. And we actually came up with several pairs of functions PQ for which QX minus PY was 1. And you're free to use any of those. Let's see here. P equals, I think, minus y over 2, and Q equals x over 2 was one of them. P equals 0 and Q equals x was one of them. And P equals negative y and Q equals 0 was one. And somebody even came up with like 2x and 3x or something, which is also perfectly fine. 2x and 3y, I don't remember. Take any one of these pairs and use it here. So let's do the first one. And use that integral and that parameterization to calculate the area. So that was the intention. This is just an ordinary line integral. You know how to do this. dx, for example, would be the derivative of this guy. dy would be the derivative of this guy. And then this is y in here. This is x in here. What are the limits of integration in this problem?
Between
0 to 2 pi? Yeah. All right, so I'll leave that to you. Other questions? Oh, and it's nasty.
Yeah, I was gonna ask. I tried to try this, and then I got like cosine like to the 5th in my integrand, and decided I didn't want to do that. So I did it a different way that was simpler.
I can't remember if I thought you got even powers.
That too, but if you take out a cosine t sine t from each term, it gets the cosine to the 4th plus sine to the 4th.
Oh, so it does simplify.
Yeah.
Which pair did you use?
I use that.
This pair? So maybe this pair is easier than some of these other ones. Did you use this pair also?
No, I didn't. I don't think I actually ended up parameterizing because I used u to the 3rd and then v to the 3rd, and then I put it in 4.
You'd have to show me.
4, yeah.
Okay. Anyway, so I don't know how bad the trig integrals are here, but just a rule of thumb, I mean, you should be able to do some trig integrals. For example, the homework that I just passed back to you, I think there was a, oh boy, I can't remember what it was. There was a sine cubed. And there was also an integration by parts. There was like a t cosine t. Those are ones that you should be able to do. Like odd powers of sine and cosine you should be able to handle, because all you have to do is pull off one of the powers, and what's left behind you can hit with a Pythagorean identity, and it's really straightforward. Even powers, you should be able to do sine squared and cosine squared without too much effort. Sine to the 4th, cosine to the 4th, they're a pain. Sine to the 6th, cosine to the 6th, also a pain. So I'll try to avoid them. In fact, I will avoid them in an exam. If you ever encounter one of those guys in homework, there are these so-called reduction formulas, which you may or may not be familiar with. Let me pull one up. So the even powers, you've seen these. These other even powers, what you can do is you can, say you have sine to the fourth. So n is 4. So you can put n in there, that makes that sine cubed. You've got 3 over 4 here, and then you've got sine squared. So it takes this integral, which had a sine to the fourth in it, it gives you a bunch of gobbledygook, and then an integral sine squared. Sine squared you can do. This is a so-called reduction formula. If you have a sixth power, it gets a little more complicated, and I won't hit you with that, but just so you know it's here. You have a 6 here, so n is 6. You do all of this stuff, you get gobbledygook, you have sine to the fourth. Now you go back over here and you do it with 4. And you do all this gobbledygook, and you've got a 2 here. That one you can integrate. So it's a reduction formula. You keep applying it recursively, getting more and more gobbledygook until you get down to something that you can actually integrate. So-called reduction formula. All right, other questions on the homework? Go away. All right, let's go talk about the topic of the day then. So today, I like today's topic. As you may or may not know, I like that boundary between geometry and calculus. I like learning things about geometry and thinking about geometric ideas in the context of calculus. Today I'm going to introduce some notation, and then I'm going to recast Green's theorem in a way that makes a lot of geometric sense, in a way that it didn't make sense perhaps before. Green's theorem up to this point is really just an algebraic identity, and by algebraic I mean it's just a collection of symbols that happen to work. And when you did your homework over the last 48 hours, that's what you were doing. You were looking at an integral, you were identifying p and q, and then you were rewriting the integral just pushing around symbols. And I dare say there wasn't a whole lot of geometric intuition developed about what was going on. You really were exploring the computational side of Green's theorem. Today, with the introduction of these two new concepts, the divergence and the curl, we get to bring a really vivid geometric picture to what's going on with Green's theorem. So to start, what I'm going to do is introduce an operator. So let's talk about this. This is the divergence and curl operators. And in fact, both of these operators are defined in terms of yet another operator. And this is going to be your first introduction to operator notation. So I want to consider this symbol, this upside down triangle, which actually has a name. Does anybody know its name? Sorry? It's not Del. I mean the symbol. Does anybody know the name of the symbol? It's called a nabla. So the upside down triangle is called the nabla. Do you know what the right side up triangle is called? A delta, yes, it's a capital delta. The upside down one is called the nabla. This is an unusual collection of symbols. This is a collection of symbols that you probably haven't seen before, because what I'm presenting you with are empty partial derivatives. So they represent the action of taking a partial derivative, but you're not actually doing anything. Okay, so this empty partial with respect to x means the action of taking the derivative with respect to x. How do we use this notation? Well, this notation was introduced by mathematicians. It's probably, I don't know, I would wager it goes almost back to Leibniz in the early 1700s. To essentially take calculus and make it look more like just regular old algebra, regular old multiplication. And so it's been a handy notation over the years, and this is, like I said, this is probably the first time you've really run into it. Let me show you how it works. Let's let f, a function of 3 variables, be a scalar function. So what do I mean by that? I mean, I plug in 3 numbers, x, y, and z, and I get out a number. Not a vector, but a number. I can consider this thing oh, I don't want to put that dot there. I'm just going to put f there. I can write something like this, and the way that I want to think about this as, I want to think of this as a vector times a scalar. Now, if this were just a regular old vector times a scalar, how do you multiply a vector by a scalar? What's the actual process that you go through? I distribute it across the coordinates, right? That's what I want to do here. And I want to distribute it across the vector from the right. And what I get as it goes across the vector from the right-hand side, I distribute it onto this, onto this, onto this. What I have is an f sitting to the right of this empty partial, an f sitting next to this one, and an f sitting next to this one. And then the way the operator notation works is it says, wow, now I've got something to work on. So I'm going to just take the derivative of that with respect to x, or with respect to y, or with respect to z. So what it does is it kind of fools the mathematician into thinking that he's working with multiplication when really he's still differentiating. It's weird, but it's useful. And it's important that you keep track of the order in which you do this. For example, this doesn't really make sense. Why? Because when f distributes through the vector, it ends up behind the partials on the left-hand side, and we don't really know what to do with that. So new rules, new symbols, new ideas. Just roll with it for a little while. And this thing is secretly just the gradient, right? That's just the gradient of f. So what we can do is we can represent the gradient of f as simply nabla times f.
So it's not commutative, so you can't flip it around.
Right. Yeah, I think that's a safe way to say it at the moment anyway. Okay, well, let's see what else we can do with nabla. Well, let's try dot product. Let f be a vector field with the usual component functions, p, q, and r. And then let's look at nabla dot f. Like that. Well, remember how the dot product works. You multiply the components and then you add. Except in this case, when we multiply components, what we're really doing is partial differentiation. So we multiply the components. and we add, and we get something that looks like this. Partial of p with respect to x plus partial of q with respect to y plus partial of r with respect to z. And I want to note here that this is a scalar result. So just like the regular dot product that takes two vectors and spits out a scalar, this operation with nabla takes two vectors and spits out a scalar. And this is called the divergence of f. All right. You won't be surprised to learn that we can do a cross product also. Okay, the cross product of nabla with f, denoted in the usual way, nabla cross f, you would compute in the usual way. So you have I, j, k, you have the partials, yeah, that's a j, and then you have the components of f, p, q, and r. And then you compute this in the way that you did back in whatever that was, chapter 12, chapter 13. Right? To find the I component, you blot out the I column, and then you do this times this minus this times this. And you go all the way across, so let's do that. So we blot out the I column, we get r sub y, I'm using that subscript notation for my partial derivatives, minus q sub z, I, minus, remember there's a minus sign that comes with the j component, r sub x minus p sub z, j, and finally the k component, q sub x minus p sub y. Does everybody remember what I, j, and k are? Those standard unit normal vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. All right. It's a complicated expression. God knows what it means, but we do you see anything in there that's interesting? Qx minus py, which is precisely the integrand for the double integral in Green's theorem. The others? How about the others? What about, do you see any connection to stuff that you did earlier in the week with those other guys, Lane? Yeah, in fact, those are the pairs that we see in the test for conservativeness. In fact, what can you say about the curl of a conservative vector field? 0, because if it's conservative, it's going to pass those three tests, which are going to give you zeros in each of the three components. Yeah? So it may seem like I'm just dumping a whole pile of symbols on your heads, but in fact, these symbols actually are intimately connected with some of the stuff that we've done earlier, and we just haven't had the equipment at our disposal to really see what's going on. So let me note here a couple of things. So this is the Green's theorem integrand. All of these guys are from the 3D test for conservativeness. So there are definitely some connections there. We don't really see what's going on with the divergence other than it just is what it is, the sum of these partial derivatives. But the cross product certainly has some intriguing pieces to it. That would be it would be nice to know how it's connected. Okay, so before I do that, so I've introduced the divergence, I've introduced the cross product. We already knew about the gradient. Before I go on and show you how these guys fit into Green's theorem, I want to talk a little bit about the physical significance of these quantities, the divergence and the curl in particular. Okay. So if I just want to get 2 words into your head, this is sort of, what's the word? Compression. And this is rotation. So if I had to pick 2 words to describe these 2 quantities, I'll choose compression for divergence and rotation for curl. In fact, divergence is a good word for divergence, if I had to pick a word. Okay? But I decided to pick another one because we already used divergence. And curl is kind of a good word for curl. If you think about curl as kind of going around something. So they are aptly named already. I'm just throwing a couple other words up there at you. All right, let's talk about compression. So the divergence of F So let me pull up my vector field plotter here and try to describe to you qualitatively what I'm talking about. Here's a nice simple vector field. Radial, always pointing away from the origin. And what I want you to do is pretend that this is an instantaneous moment of time in some fluid flow, for example. And let's pick a point. Let's pick a point right here. If you go a little bit to the left of the point, the flow is always to the left here, right? Along this whole axis, the flow is to the left, at least on the negative axis. If I'm sitting at a point right here and I go a little bit to the left, the flow is increasing. If I go a little bit to the right, the flow is decreasing. So if I were thinking about sort of material flowing into that location and material flowing out of that location, is there more flowing in or out? It's a very subtle question. Is there more flowing in or out? We had 2 outs over here. So I'm sitting right here. These arrows indicate that stuff is flowing into this point. These arrows indicate there's stuff flowing out of this point. So is there more flowing in or out? You were right the first time.
Really?
Yes.
How do you not end up with?
Let me try to explain. Let's pretend I'm sitting right here at this point, a little bit to the left of me. So on this side, a little bit to the left of me, that flow vector is bigger than a little bit to the right. And so at that position, there's more stuff leaving over here than there is coming in right at that moment. And so it's out. So that area of this field, whatever this is describing, is somehow expanding. Right? There's more stuff leaving. It's becoming less dense, I guess, is another way to look at it at that point. And that's actually true throughout this entire field. Okay, if you look at this entire field, you pick any point, it's expanding. And that kind of makes sense because this looks like a big explosion, right? You're taking something and like this, it's taking up less space. So in fact, everything is decompressing. How can I get one where everything is compressing? If I put a minus sign in there, everything's going to flip around, and I'm going to have an implosion. And then we'll look really closely at it and convince ourselves. we'll look really closly at it and convince ourselves that there's actual compression going on. So again, let's pick a point right here. There's more stuff coming into this point than there is leaving. So there's an accumulation of stuff there. And that's compression. All right, let's look at it one more, and then I will let's do something like I plus j. And let's make the scale like a half or something. What about this guy? Are there any places where there's stuff accumulating or stuff expanding? No, because if I pick any, these are all constant, right? If I pick any point, the stuff flowing into that point is exactly equal to the stuff flowing out. So there's, it's conserved in a sense. That's not what a conservative field is, although this is a conservative field. The whatever this represents is conserved. Okay, so divergence, typically we say places of compression, places where stuff is accumulating, we're going to call that negative divergence, and stuff where it's expanding, we're going to call that positive divergence. All right. And that makes sense, right? Because the word is divergence. So if stuff is coming together, it's not diverging, right? So you want that to be negative. All right. So that's my brief discussion of divergence. Let's talk about curl. So this measures the circulation around a point in the field. So let me see if I can get myself a field with a lot of curl to it. Let's see here. Let's do yi plus -1 xj. And let me change the scale back to something more reasonable. Okay. So when you think curl, you want to think rotation. And it certainly looks like there's a lot of rotation in this field. But remember, it's not the rotation of the whole field. It's look at a point and think about, is there some sort of net rotation there? There is a way to think about this. There is a thought experiment that you can go through to help you understand what the curl is at a particular point. Let's place a little sphere right here. Little sphere right at that point. And let's pretend these are force vectors that want to push on the sphere. So here's your little sphere right here. Over here, there's a little force vector that wants to twist the sphere clockwise, right? So there's a force vector flowing this way that wants to spin it around clockwise. Everybody see that? And over here, there's a force vector flowing past that wants to spin the thing counterclockwise. So there's one on this side, there's one on this side. They're both flowing in the same direction. And if they're equal, that sphere isn't going to turn, right? Because this is going to want to push it this way, this guy's going to want to push it this way, and if they're equal, it's just going to sit there. Are they equal? They're not equal, right? Because these vectors get bigger as you go away from the origin. So the one out here is going to beat the one in here. And what's the net rotation going to be? Clockwise. There's going to be a net clockwise rotation. That's what curl is measuring, roughly speaking. Dip a little sphere in there, look at the force vectors, and try to figure out which way it's going to rotate. The curl follows the right-hand rule. Notice that the curl is a vector quantity. rotation, in a sense, the rotation of that little sphere is a vector quantity. Because a sphere, right, it's going to rotate and it has an axis of rotation. For example, the Earth, big sphere, it rotates, it has an axis of rotation. The direction of that axis of rotation is what the curl is the direction of the curl. And the magnitude of the curl is sort of how much it wants to turn, how fast it wants to turn. And in this simple example where you have a vector on this side and a vector on this side, you can see that the axis of rotation is probably going to come out of the board at you. Yeah. And it's probably not going to be super fast because there's not that much imbalance between this vector and this vector. But if there's a lot of imbalance, like a really short vector and a really long vector, then you're going to get a lot of spin. Okay, again, I'm speaking very loosely here. A lot of this I've got just from teaching this over the years, but there's also a really nice couple of links here that David provides in the book. And let me just point you to those, and I'll let you go explore those on your own. So at the top of the second page of the section, there are these two links that talk more about the physical meaning of these two quantities. And if you're into physics and into engineering, it's certainly worth your while to develop some intuition about these quantities. All right, but that's as far as I'm going to go with the intuition. What I want to do now is talk about, I want to re-express Green's theorem using these quantities. Or these symbols, let's say symbols. All right. When I write this integral, what physical quantity does that represent to you? It's work. It's work, right? I want to write this in a slightly different way. I'm going to go back a little bit further and just write it as f dotted with t ds. Well, what is t? This is the unit tangent along C. Okay, so we have the curve C, and say it's oriented like that. At every point on C, there's this tangent vector, right? Also at that point, because this particle is moving in a force field, also at this point is some force, F, right? If I want to know how much of the force is in the tangential direction, how do I figure that out? Yeah. Yeah, the projection, and the way to do the projection is with the dot product, right? So F dot T is a measure of so that's another way of thinking about work. Right? Work is F dot dr. Work is the component of the force in the tangential direction. And so another way of writing this integral is F dot T ds. T being the tangent vector along the curve. So just different symbols for the same thing. Let's talk about what this means in the context of a closed curve. So now we've got a closed curve, and we want to look at tangents around the curve. T around D. If you sum this up, this is kind of a measure of rotation around the set. Okay. Well, let's look at Green's theorem again from this new perspective. So f dot t ds we know is just this guy. F dot dr, which we know is just this guy. P dx plus q dy, which we know is just this guy. Qx minus py dA. And we recognized earlier that this integrand appeared in the curl. This was in fact the k component of the curl. So I'm going to rewrite this in yet another way. So if I take the curl of f and dot it with k, I pick off the k component of the curl, right? And if you look back in your notes and you go look at the kth component, isn't that exactly qx minus py? Okay, so you should believe this then, that this is equal to all of this and hence is equal to this by Green's theorem. This is really interesting because what it says is if I look at a point here, there's some rotation around that point due to the field. And then let's look at a point that's nearby, say this guy. If it's nearby, since this vector field is a continuous vector field, if it's nearby, you can expect the rotation around that point to be the same, in the same direction. What's going to happen when the rotation around this guy hits the rotation around this guy between them? What's going to happen with the forces? They're going to cancel, right? So cancellation happens. So cancellation happens between nearby points. So the rotational stuff cancels between adjacent points, and of course there's another point over here that's going to cancel with this, and there's a point up here that's going to cancel. So throughout this entire domain there's a lot of cancellation, right? So can I just use this loose argument to say, oh, well, the integral of the curl across the whole thing is 0? What's wrong with saying that, Nick?
Because where it intersects, where the rotation intersects the bound of D, nothing's going to cancel.
At the boundary, there are points. So let's look at one of these guys out here and look at the rotation around it. It doesn't have a partner up here to cancel its rotation. So here, when I do the integral and I get to the boundary, there's going to be uncanceled rotations. And you'll not be surprised to learn, in fact, that the sum of that uncanceled rotation is exactly equal to the sum of the force around the boundary in the tangential direction. That's an intuitive explanation for why this is true. And that gives me the curl. Let me show you a similar explanation for divergence. So just like f dot t ds, I want to look at the integral around d of f dot n ds, where this is the normal. K is 0, 0, 1. So now I want to think about f dot n normal to the boundary, right? Look, I mean, it makes sense. If I want to talk about t here, it makes sense that I might want to also talk about n. Because every point on the boundary is going to have a tangential vector and a normal vector, right? And we're just going to agree that we'll use the outward n. We have two choices for n, the inward pointing one and the outward pointing one. We're going to use the outward pointing one. This is akin to using the right-hand rule. So in the same way that we arbitrarily choose the right-hand rule, we're going to arbitrarily choose the outward pointing normal. And in fact, it's consistent with the right-hand rule. So it makes sense, right? Maybe instead of finding the tangential component of f around the boundary, maybe I want to find the normal component of f around the boundary. What's interesting about that is the normal component tells you how much of f is flowing across the boundary, and the tangential component tells you how much is not flowing across the boundary, how much is flowing tangent to the boundary. Well, let's see if we can't get a grip on this. Let's see. I'm not sure why I just lost my train of thought. Yeah, in fact, I won't bother to prove it. What I'm going to do is I'm going to show you. I've got the proof here, but I think for the sake of time, what I'd like to do is instead talk about a similar picture here. Let's pretend we've got a point where it's decompressing. Okay, so we have positive divergence at this point. And let's pretend we've got a nearby point. If it's nearby, then you can expect it to also be decompressing. So stuff is flowing away from it. What's going to happen between these two guys? Cancellation again. So the nearby divergence sort of cancels with itself. And that happens throughout the whole domain. And then I ask the same question. Well, then the divergence across the whole domain has to be 0. And Nick says no, because what about the boundaries? And he's right. The boundary stuff doesn't cancel. The boundary stuff doesn't have a partner to cancel with. And so what you're left with is the integral over the whole region of the divergence of f dA is the same as, let's talk about this guy here, and let's pretend that there's divergence, is essentially a measure of how much stuff is flowing across the boundary. So the book will give you a symbolic proof of each of these, and I'll leave that to you to read. This is a heuristic argument for why this is the case. So one of these integrals, the n integral measures the flow or the flux across the boundary, and the t integral measures what's running tangent to the boundary.
I guess it's not really important, but wouldn't the non-normal vectors get canceled by adjacent points?
Yes. And so, I mean, I guess I sketched them in there just to, but yeah, they would be gone.
Even on the boundaries?
Yes. It's just that one normal guy that, yeah, would survive, which is why f dot n. Okay. All right, let's do some examples here. 16.5.3. I'll show you how some of these work. Okay, so in problem 3, you're given the force field ay squared plus bx squared. You're given this region D, which is actually a triangular region, and you're asked to compute the tangential forces around the boundary and the normal forces around the boundary. And the book is almost always going to use F dot dr. The F dot t stuff is really just my notation. So the book will always use F dot dr to talk about the tangential stuff, and then F dot n for the normal stuff. This is really just a matter of applying the Green's theorem in this particular context. So let's do the first one. So ay squared bx squared. And the region was that. And we're asked to compute F dot dr around the boundary. Well, Green's theorem says that's the curl of F dotted with the standard unit normal vector in the z direction, dA. So to complete this integral, the first thing we need to do is to find the curl of F dotted with k. Well, the curl of F is denoted using this mnemonic. Now, I could go through and I could do the whole curl, and then I could dot it with k, or I could be smarter and do what?
F is a scalar function.
F is a vector function.
Oh, okay.
F dot k. Just take the k component, right? Because when I dot it with k, whatever was in the I component is going to get wiped out. Whatever's in the j component is going to get wiped out, because remember what k is. So I don't need to compute I don't need to compute j, I just need to compute k. So let's do that. So k, I blot out the k column. That means partial of this with respect to x minus the partial of this with respect to y. And I'm done, at least with that part of it. So I take that expression and I return to the integral, and I have to put in some limits of integration and so forth. And the limits are practically handed to you on a silver platter. Y goes from 0 to x. X goes from 0 to 1. And that's an integral that you know how to do, so I'll leave that to you. Let's do the other one. So the other one, the complement of this integral, is f dot n ds. And Green's theorem tells us that f dot n ds is just the divergence of f dA. So that means we have to compute the divergence of f before we continue. What's the divergence of f? Dot product? Don't be afraid to say it. It's 0, yes. It's 0. So this is, this vector field has no divergence. That makes this integral fairly easy. What is it? It's 0. Let's have a look at let's have a look at this vector field just for a particular a and b. Let's try just y squared x squared or something and see what it looks like. And I guess I can knock down the scale a little bit here. That's a little better, I suppose. Yeah, maybe too much. All right. So this is definitely a strange-looking vector field. The claim is there's no divergence in this vector field. There are no places that are getting more or less compressed. There is some curl in this vector field. The curl varies from point to point, but there's some curl. It's hard to just stare at this and think that there's no divergence here. Here, at some point, you just got to trust the calculation. Okay, but essentially, if you pick a point in space here, say right here, the stuff flowing in and the stuff flowing out balance.
So why does it look like that doesn't happen on the diagonal? Right when the flow seems to split, it seems like there's more coming in.
Yeah, I think that's a good question. Let me see if I can. Figure out a reason for that.
Well, if you were to imagine it as water, it'd be spreading out, so you wouldn't have to have as much in one direction. Does that make sense? And when it's coming back, you have it sort of funneling in, so you need more in that other direction.
I think the thing, Henry, that you have to deal with is all of those other fields that I was looking at, the flow lines, the flow along the flows were straight lines. And what's weird about this one is, yeah, this flow's a straight line, but very near it, there's curved stuff, and so it doesn't suffice to just look like in those other examples that I was looking at, all of the flow lines were just parallel lines, and so I could isolate the net flow just by considering the horizontal action or the vertical action. But here, that's hard to do because I agree that the flow line here is a diagonal line. But if you step away from this just a little bit, then there's stuff being carried away that wasn't happening in the other one. And so I wish I could explain it to you better than that. And that's why I said you kind of have to just trust the calculation. These flow lines there's only one straight flow line in this whole thing. The rest of them are all sort of flowing away. And so it's more complicated when I look at this point and I see, yeah, there's more stuff coming in than there is leaving. That's not entirely true because there is more stuff coming in along this line than leaving, but there's stuff leaving this point in these directions as well. And it balances out. But it's very complex. Was there another hand over here? Okay. Yeah. All right. So, in fact, let's talk a little bit more about that. There are a couple of identities that I want to share with you in the remaining 10 minutes. So there are two theorems that the book presents. One says that the curl of the gradient of some scalar function f is 0. And the other one says that the divergence of the curl of a function is 0. These are two important theoretical identities that you would use in proofs. Rarely would you use these in calculation, but you would use these in proofs. This is really a test for, this first one gives you a test for conservativeness. In other words, from one, we see that if the curl of some vector field equals 0, then f is conservative. That's not a proof, it's just a strong suggestion. So conservative fields can't have rotation in them. So for example, the most common conservative field that we have experience with is gravity. And if you pick a point in space and you look at those force vectors, right? This point is being acted on by the Earth in large majority. There's nothing twisty about that force. It's just straight to the center of the Earth. No curl involved. All divergence. So in fact, you can use this as a test for conservativeness. It's a toss-up as to whether this is a better test than the one that you already know, because ultimately you have to compute all of those partial derivatives anyway. The other one, let me think about this. If you take the curl of f, you take the curl of a vector field, in a sense what you do is you remove all of the divergence from it. And you're left with nothing but rotation. And so when you do the divergence on that thing, you get 0. Okay, one last comment. If the divergence of a vector field is 0, this is called an incompressible vector field. And in physics and chemistry, what's the most common incompressible substance you know? Water. Water, right? Does everybody know that that water is incompressible? Okay. Water is incompressible, if you didn't know. What's interesting about that is, let's do a thought experiment. You go to the Mill Creek channel and you're watching the water flow through the channel, and you snap and you stop time. And then what you do is you attach little velocity vectors to every one of the water molecules flowing down that channel. And then you find some magical function that describes all of those vectors. And you take the divergence of that function, you'll get 0. No matter how crazy the water, well, not how crazy the water is, but within reason, no matter how fast, slow, twisty, turny, whatever that water flows, you stop time, you set up that picture, and you take the divergence of that vector field, you will always get 0, because water is incompressible. You can't have a place where water is building up and another place where water is spreading out. Water's just water. It doesn't get denser and it doesn't get less dense. And so it can only flow in an incompressible way. It can only flow in an incompressible way. This is a very powerful mathematical tool when you're studying the Navier-Stokes equations, for example, which describes fluid flow. The Navier-Stokes equations are very general. They describe not only how water flows, but they describe how air flows across, say, a car moving down the highway. The Navier-Stokes equations actually have a divergence term in there, and they become dramatically simpler when you use them to model water than when you use them to model air. Air is much harder to model using computers, using the Navier-Stokes equations, because air is compressible. Air can flow in ways in which air builds up in one place and it spreads out in another place. And that makes the behavior of air fundamentally different than the behavior of water, and hence much more complicated. And in fact, it's this compressibility of air which really gives us weather. There's not much weather in the ocean underwater. Okay, I don't know if you've ever, you swim around, you're out in the surf and you go underwater and all that craziness is happening above you. Waves are crashing to the shore and things are relatively calm underwater, right? That's the result of the incompressibility. Whereas you're up here out in the atmosphere and you get tornadoes and hurricanes and just really windy days and things like that. That's all due to the fact that air is compressible. It's much more complicated. With that, I will leave you until Friday.
I mean, it does. You just can't have that correlation.
Yo.
I mean, you Friday or when we get back?